Section 2, let's look at the fixture. Let's drill down into our lowest level fixture submodule, where we found it convenient to encapsulate the DUT itself, any analog signals entering or leaving the DUT, as well as any X-model instrumentation we needed to generate stimuli or check response. It all starts at this interface port named frequency in. This brings in this bundle of signals coming from the driver, one of which is our randomized real valued frequency variable fReal. Before we can go any further, we need to convert it from an ordinary SystemVerilog real value to the corresponding X model type xReal. This packs in a little extra information that enables analog quantities to be simulated in an event-driven simulator. So we need to connect this simple converter primitive. But once we've done that, all we've got is a simple constant. How do we change that into a waveform? Well, we can integrate over time, converting the constant into a ramp. Here we're using a particular flavor of the integrator block. This integrates modulo 1. So the ramp rises up to unity, drops back to 0, rises to unity, starts all over again. Bingo, we've got a sawtooth function. We scale it, one of the simplest X model primitives, by the factor 2 pi. We've now got omega t, the exact argument we need to generate the desired sinusoid. We feed it into the sine func primitive, and that generates the sine omega t signal we need to apply to the DUT. By the way, this has two primitives. You can choose sine or cosine behavior, and it also has an amplitude, and we set that parameter to 100 millivolts, which was within the specified range of our 9-transistor op-amp. So with a few primitives, we've now generated an analog stimulus to the DUT. Let's reinforce that by taking these same few primitives and wiring them together to generate two quadrature signals, a sine and cosine of the same frequency fxReal. So let's take a few seconds to think about that. Here's the answer. Here we're seeing two instances of sine func, f0 and f1. One is parameterized to generate a cosine, the other is a sine. They take the same sawtooth input we saw scaled and integrated over time. And this one generates a cosine I, this generates a sine Q. So using the rich set of over 100 X model primitives, you can create any analog stimuli that you wish. Let's look at the mode. This is much simpler. Through the same interface port freq in, we're bringing in the enumerated mode. Let's defer for now the bypass testing of the filter. We'll look at that in section 6. So for now, we'll deassert the most significant bit. So we're only concerned with these 3 mode bits, giving us a choice of 8 enumerated modes, and we can apply them directly to the filter inputs. Any necessary bit to X bit conversion is done inside the filter. These next 4 slides demonstrate a SystemVerilog trick. The modes can easily repeat, since we only have 8 of them, and they each have a 12.5% chance of coming up. You can get 2 or even more M7s even in a short sequence like this, which is undesirable. So we might think of using the qualifier rand-C, C for cyclic, which avoids repetition. And that's fine for simple examples, but it has some limitations. Number one, suppose you're analog IP was more complex, and instead of 3 mode bits, it had 48. Well, you're out of luck. You'll get a fatal syntax error when you read the code into the simulator. In this tool, the limit is 32 bits on a RAND-C variable. So it's not very scalable. The other limitation is that it has little persistence. We want to apply a new transaction on each rising edge of our packet clock, and that requires a new data packet each cycle. Well, the memory of used values is lost as you go from one packet to the next. So RAND-C won't do the job. Let's look at the solution. We'll look at the code here, and this is attributed to a blog by Dave Rich. He basically said, hey, you don't need to rely on RAND-C with its well-known limitations. You can use any SystemVerilog syntax you want to shape the distribution of random values. In particular, you can use a queue. So here's a queue of used values. It's like an unpacked array, but the $ tells SystemVerilog that this is a queue. You can push used mode values onto it and empty the queue. And the important thing is that it's got to be a static queue. Static is one of the most overused words in the SystemVerilog language, right up there with virtual. In this context, it simply means that every packet instantiated from this class seeds the same queue, not different copies of it. It's a static queue. So we add a constraint. We're basically telling the random number generator, hey, that random value of mode that you're about to come up with, it better not be inside the queue of already used values. And by the way, inside as an operator does know how to traverse the elements of an unpacked array. And then you'll recall the post-randomize function we used earlier. Here we add some code to it, and as soon as the used queue is almost full, has 7 values, we can, there's only one choice left in our 8 modes. We can apply that and then empty out the queues, start all over again. So slide 23, here we see a simulation where the queue fills up. It's now almost full. There's only one value, 0, remaining to be used. So we can empty the queue and start all over again. Thanks to the blog by Dave Rich. It works great. Let's switch focus to the output side of our fixture. We need to measure the amplitude of the sinusoids coming out of the filter and going into it. Divide those two to compute the actual gain. So we can instantiate a couple of instances of the measure peak-to-peak primitive. This one samples the sinusoid going in and generates the peak-to-peak amplitude that it has at any given time. This conveniently is a real value type, and we don't need to convert it. By the way, this is a typical data sheet for an X model primitive available at the Scientific Analog Support website. That's not the whole story, though, because every time we apply a new stimulus frequency to the filter, there's a transient period. We want to allow enough time for the signal to settle out. So we're going to measure the peak-to-peak amplitude over a fixed time span delimited by a starting trigger and an ending trigger. And we can use ordinary SystemVerilog code inside the fixture to generate these two trigger signals. I've called them tick and talk. So we allow plenty of time for the transients to settle out, and then this yellow highlighted time span called dwell here, it's a parameter of at least 100 microseconds, and so the peak-to-peak measurement is done during this dwell time. Trigger signals in general, either edge is active. These are ordinary bit signals, so we have to convert them to X bit using these converter primitives, giving us tick X and talk X fit into the primitive. some primitives in XModel do directly offer X-bit triggers. So here's the complete peak-to-peak amplitude subcircuit, starting from the interface port, which brings in the packet clock. We have ordinary SystemVerilog code generating the bit type signals tick and talk, convert them, feed them to both measurement primitives, and that gives us the peak-to-peak amplitudes we need coming out of and going into the filter. We divide them to generate the actual filter gain. This is a preview of code we're going to look at in more detail in section 5 on the scoreboard. Summarize, the Fixture submodule is a convenient way to encapsulate the DUT itself and various XModel primitives needed to apply stimulus and measure response. It's a good idea to encapsulate all signals of X-real and X-bit type inside of this fixture and any converter primitives you need. The fixture can include arbitrary SystemVerilog code like the initial block we just saw to process data. And key point, the XModel types X-real and X-bit, which are defined in a header file, xmodel.h, are actually packed structures, and they contain not only a member value, which is of type long-int and bit respectively, but also additional information that keeps track of events, and this enables the simulation of analog quantities on an ordinary event-driven logic simulator. Okay, in the next section, we'll go up the hierarchy and look at a higher level object, the sequence component.